All right, now we're going to look at the derivative of the exponential function. The derivative of the exponential function of base b is given by b to the u times ln b times du dx. So you'll note first thing we do is just repeat the function itself. We multiply by the derivative, we multiply by the natural log of that base, and then of course the chain rule ever present. If we have the natural exponential function, the derivative of e to the stuff is just e to the stuff times du dx. That is, of course, because ln of e is equal to 1, right? Log base e of e is equal to 1. We're going to do some examples, get some practice with this formula. So if I want to find dy dx for this exponential function, 2 to the 4x, note that an exponential function, of course, has a constant base. In this case, that base is 2, and then we're raising it to a power. We have a variable in the exponent. So this property, or this formula here, tells us that dy dx, I start by repeating the function itself, 2 to the 4x power. I'm going to multiply by the natural log of the base, so ln of 2, and then times the derivative of the stuff inside. Inside in this case means the derivative of the exponent, so that's times 4. And just cleaning it up a little bit, putting my coefficient in front, I've got 4 ln 2 times 2 to the 4x. The natural base is far more common than other bases, so you'll probably see the e to the stuff a lot more than you will 2 to the stuff or 3 to the stuff. So in this example, we're going to find the derivative of ln of sine of e to the 5x. So I definitely have an exponential function in there, right? It's tucked inside the sine function. But here we just have a composition of functions. We've got a 5x function stuffed inside an exponential function, stuffed inside a sine function, stuffed inside a ln function. So this problem is going to be all about the chain rule. My outermost function is ln, so that's what's going to determine how I start this derivative process. Dy dx, if I'm finding the derivative of ln of stuff, it's 1 over the stuff. So I have 1 over sine of e to the 5x. Now the chain rule says I'm going to multiply by the derivative of the stuff. So the derivative of sine of that stuff is cosine of the stuff times the derivative of what's inside the sine function. So times the derivative of e to the 5x. Here's where we're going to use that new formula. So that's going to be e to the 5x times the derivative of the stuff in the exponent. So times 5. This, again, we could see why we call it a chain rule. There are many links to this chain. 1, 2, 3 links to this chain. Now we're going to simplify a bit. Cosine over sine. Again, note that the arguments inside the cosine and sine functions are the same, right? It's e to the 5x. So that means I can simplify cosine over sine is cotangent. And then I have these other factors I'm going to bring down. So I've got 5 e to the 5x times cotan of e to the 5x. All right, let's do another one. Here we're going to find the slope of a tangent line when x is 1.275. So slope of a tangent line means, of course, we're going to find dy dx and then evaluate it at that point. The form of this function, I've got 3 times e to the 2x divided by x squared plus 1, so this is a quotient rule problem. F is always the function on top, so that is 3e to the 2x. So when we find f prime, I'm going to have 3 times e to the 2x, right? I repeat the function, and then the chain rule says times the derivative of what's inside times 2, so it'll be 6 e to the 2x for f prime. Our g function is x squared plus 1, so g prime is 2x. Now let's put this together. Dy dx equals g times f prime. So if I multiply these together, I've got 6e to the 2x times x squared plus 1 minus f times g prime. So if I multiply those two together, I get 6x 6x e to the 2x. This is all over g squared, so that is the square of x squared plus 1. To simplify a little bit, we just want to evaluate this when x is 1.275, so I suppose we could do that now. I think it'll be a little bit simpler if we do some factoring up top. So I'm going to take out 6 times e to the 2x in the numerator. And then inside I've got x squared plus 1 minus x. I don't think there's a whole lot more we can do to simplify. So now it's just up to us to evaluate. So dy dx. Okay, so 6 times e to the 2 times 1.275, open up parentheses, close the parentheses, divide by, I'm going to put the bottom. So you open up parentheses, 1.275 squared plus 1, close parentheses, square, gives us about 15.05. So there's our M tan.